routine core analysis and SCAD. So I'm not going to talk anything today about enhanced oil recovery. However, enhanced oil recovery, like the lab work of enhanced oil recovery, is a part of core analysis. This is a picture of myself in 2017. I was much younger that time. I was working on a core flooding system at the UAE University Core Lab. On your screen, you can see seminar outline, right?
True.
Okay, so I will start with no further ado. Okay, the outlines of the seminar is basically the core analysis process. We start with cleaning and saturation determination, and then liquid density and viscosity, then porosity of the core or rock, and then resistivity, surface tension and interfacial tension. And then I will talk about the contact angle and tweetability, then a little bit about pressure, capillary pressure, and then I will end with permeability. So and the aim of this seminar is to give education about working in a core analysis lab, and it will hopefully it will promote awareness of rule and functions of core analysis lab. So, sorry, I will make this small. Okay, my references are the core lab, like core laboratories, reservoir optimization, and Society of Petroleum Engineers (SPE), and the Society of Core Analysts, the SCA. I took my material from those three sources. So let's start with the seminar. Okay, knowledge of petrophysics and hydrodynamic properties of reservoir rocks are of fundamental importance to the petroleum engineer, and especially for the reservoir engineer. As you can see here, this picture is the picture of the drilling bit. That drilling bit is special designed to make cores. How the core look like? It looks like those barrels. It will be cylindrical, right angle cylindrical shape. Hopefully, if it's not broken, as you can see here, this one is broken. It is rubble. Okay, because of some technical issues. However, the good one will be right angle cylindrical shape. The diameter will be something between 4 inches or 3 inches, depends upon the diameter of the drilling bit, and the length usually it cuts into 1 meter. Each one of those will cut into 1 meter, and then they will put them in a box. If you come closer, see here at the end of the box, there is a piece of sponge. Okay, so this sponge that the box is wooden box, and there is two pieces of sponge and one piece of sponge on the bottom, so the rock or the core will be safe during the transportation. As you can see here in the pictures, those samples were taken from an oil reservoir because they are black already, they are saturated with oil. As I said, in core analysis, we have routine core analysis, and we have the special core analysis or advanced core analysis. For routine core analysis, we call it RCA. Okay, so what we measure porosity, means the storage capacity or storage capacitance of the rock sample. And then also we measure permeability. Permeability is the flow capacitance of the core sample. And we study the saturation of oil, gas, and water. Of course, we directly measure the saturation of water, and then we calculate the saturation of Hydrocarbons means oil. I will talk about that in more details later on. Also, we study the lithology. What is lithology? Lithology is rock type and characteristics like fractures and layering, etc. Of course, here in this webinar, I'm not going to talk about lithology, okay, because that is another field. It needs another webinar. And in addition to routine core analysis, there are supplementary measurement. Supplementary measurement. The first one is vertical permeability. See here, I'm going back. Permeability. When you hear permeability, that is the horizontal permeability. But for vertical permeability, we always have to refer to that to vertical permeability. It measures the permeability in the upward. Okay. Sometimes they say in the upward and the horizontal is the horizontally, okay, and vertical is vertically. Actually, it's not always like that because horizontal means it is parallel to the bedding. Vertical is cross the bedding. Okay, keep that in mind, please. And there is another supplementary measurement that is core gamma surface log. We use it to correlate cores and logs, and also depths. Matrix density, calibrate the density log. You know, you are always all aware of the LWD, log while drilling. So they do measurement during while drilling, and then after they are finished, we take the sample, we measure the density, we also measure the core gamma. Sorry, the core gamma log, and then we match our measurement with the well measurement and see how much accurate is the measurement, and we can match then the depths. And oil and water analysis. In oil and water analysis, we measure or we obtain the density, viscosity, interfacial tension, and the compensation, especially for water, for like formation water, because we need to synthesize that water in our lab to prepare what we call it the formation water, and then after that we will saturate our core samples with this water and start the flooding tests. Okay, now that was the routine core analysis. Now we will go to the special core analysis or advanced core analysis. We call it SCAL, SCAL, SCAL. In special core analysis, we measure compressibility of, see, most of people say compressibility of rock. Actually, we don't study compressibility of rock. We study compressibility of pores. We study compressibility of pores, not rock. Compressibility of rock, that is rock mechanics. Okay, just to be clear. But you know, it is a common mistake. Okay, and also the special core analysis include the petrographical studies. It include wettability. Later on, I will talk about how to measure wettability or how to obtain the wettability. Now, wettability usually measured or obtained by studying the contact angle and the wettability index. Later on, I will talk in more details. And then capillarity means capillary pressure versus saturation. There are also many ways to study or to obtain the capillarity. And then acoustic tests. I'm not going to talk about acoustic tests in this webinar. And then electrical tests. We run the electrical test to obtain M and N and S RI and RW, etc. Later on, I will talk in more details about those. Um, in special core analysis, we have two types of special core analysis. The first one is dynamic, and the second one is static. So for dynamic tests, it is flow studies like relative permeability and point saturation. And EOR flow tests in injectivity and residual saturation. Residual saturation is like residual oil saturation and irreducible water saturation. Both of them are residual saturation. I will start talking in more details about the routine core analysis right now, and I will start with like first thing first is core preparation. In core preparation, there are 4 steps. The first one is plugging. The second one is trimming. Third one is cleaning. Fourth one is drying. So plugging means we take the whole core, we call it whole core, that is 1 meter long and 4 inches in diameter, and then we put it here in this machine, and we plug, we drill the core, and we get plugs. Then, if you look at this picture, look here, this picture was taken during the plugging. So we place the sample here. That sample is a slabbed sample. It is 2/3. So this drill revolves, and we press it, and so it penetrates the rock, and we get this type of sample. This sample is 1.5 inch in diameter, and this one is 1 inch in diameter. Usually they take the 1 inch diameter sample for scale, but it is fine. Both are fine for scale and for routine core analysis. So that is plugging. What is trimming? Trimming is to trim the ends of the sample, so we will get the sample in right angle cylindrical shape, so we can measure length and diameter and calculate the bulk volume of the sample. Okay, sometimes after trimming we do fine trimming. After trimming we do fine trimming, so the end surface will be like crystal clear, and it will be very close to be right angle cylindrical shape. The next one, as you remember, is cleaning. Okay, cleaning the sample. What do we use to clean the sample? We use the sock slit method. Usually, or most likely, we use the sock slit apparatus. So fluid saturation is defined as the ratio of volume of fluid in given core sample to the pore volume of the sample. Okay, but before doing that, we have to clean the sample. Okay, if the sample was taken from an oil reservoir and then preserved in wax, then we can take we can place the sample in the Dean Stark unit and measure the saturation of water and oil. But I will put that in more details later on. However, here the cleaning, if the sample is not taken from the oil reservoir, then we need to clean it. Okay, so the pores will be clean of salts and they will be clean of hydrocarbons. How we clean the sample from hydrocarbon? By, if you look at this picture, this is the sock slit extractor. We place the sample here in the middle, and we place our solvent here at the bottom, and of course we boil the solvent, and there is a condenser, and the sample will be soaked in the solvent, and then by this return line, the siphon, it will go back. Sorry, the siphon is this way. This side to the right hand side, it will go down and evaporate again, soak the sample and over again. So by that, we clean the sample from hydrocarbons and from salts. What do we use to clean the samples from hydrocarbons? Usually we use toluene. Okay, and what do we use to clean the toluene and the salt is methanol. Most likely we use methanol. So maybe someone of you will ask me, how would we know that the sample is clean? Actually, there are two tests. The first one is the ultraviolet test, and the second one is the AGCL, sorry, AgNO3, the silver nitrate test. So after cleaning the sample by toluene, you take it, you take the sample and you put it under ultraviolet light. If there was a fluorescence, that means the sample is still have hydrocarbons, because hydrocarbon will produce fluorescence under the ultraviolet. So you put it back to cleaning. And once there is no fluorescence under ultraviolet or UV light, you replace this solvent here. You replace, sorry, the toluene with methanol, and you run the test for 1 day or 2 days, and then you take the sample and you put a drop of silver nitrate, AgNO3. If that drop turns into white, that white material is NaCl. That means the sample is still have salt. So you put the sample back to the suck slit. If the AgNO3 drop stay colorless, that means that your sample is clean. Sometimes you can take the sample, put it in the oven, take the weight and return it to the cleaning apparatus, put it in the oven again, take the weight. If there is no change, that means the sample is clean. Okay, but that is time consuming. So most likely we use the ultraviolet light and we use the AgNO3 or silver nitrate. Now let me go back a little bit here. If you can see, the cleaning and the saturation determination, we have 6 methods. The first one is direct inject of solvent. Direct inject of solvent, as if you are running a flow test, or for example you are running the liquid permeability test, but instead of injecting water into the sample, you will inject the solvent. Okay, but in this case you have to use a special strut that can stand for the solvent. I mean, the solvent is not corrosive to your apparatus. Now the second one is the centrifuge flushing. Okay, the third one is gas-driven solvent extraction. The fourth one is suck slit extraction, and that is the most used method. And then Dean Stark distillation extraction. Dean Stark will help you cleaning the sample and get the amount of water inside the sample, the water or the fraction of water saturation. Okay, however, there is a little bit of difference. Suck slit is more efficient than Dean Stark, because in suck slit the sample is immersed and soaked in the solvent, and then there is the vacuum distillation. Okay, now in this picture, please look carefully to this picture. That is suck slit. Okay, that is suck slit. Look carefully to this picture. That is the Dean Stark apparatus. Okay, the difference between them, the sample will be placed here, and if you can see this measuring tube here, that tube will give you the volume of water. Okay, the volume of water. So from Beanstalk, you can directly read the water saturation of the sample, and then after that, when you measure the pore volume of the sample, you subtract water from the total pore volume, and you can calculate the oil saturation of the sample. Okay, be careful if you are working with the clay sample or limestone that has clay or sandstone samples that is rich in clay. Be careful because because clay will produce more will produce its initial water. So the calculation in this case will not be accurate because in sock slate you will collect water inside the pores and the water from clay itself. Okay, and be careful that clay may crack and will damage the sample. So if the sample is clay sample or clayish sample, it's better to mount it first. Mount the sample with tin. Usually now people are using tin, not lead. Okay, mount the sample first and then you put it in cleaning. So you will protect the sample from being broken. Here is the vacuum distillation. The vacuum distillation oil and water content of core may be determined by this method, oil and water, both of them. Okay, liquid within the sample are vaporized and passed through a condensing column that is cooling by liquid nitrogen. So it is a little bit sophisticated. And up to my knowledge, is not being used. Up to my knowledge, is not being used anymore because it is expensive and it is sophisticated. So you need a very well-trained personnel to run that test. As I said, most companies, I would say, are using Dean Stark and Soxlet. Now, okay, our sample is now has been plugged, trimmed, cleaned. After the sample, once the sample is clean, we place it in the oven. There are many kind of ovens: the conventional oven, vacuum oven, what is that? Humidity controlled oven. It varies. For example, if you have clay or clayish rocks, you have to put it in a humidity controlled oven, otherwise it will break. Okay, now our sample is ready, is clean, put it in the oven, keep it there. Let's move to the liquid properties because why we want to study the liquid properties? Because we are going to saturate the sample with this liquid, means oil or water. What is density? Density is defined as the mass of fluid per unit volume. In general, it varies with pressure and temperature. So when you measure density, you have to plug it with temperature always. Of course, when we measure density of oil and water, also we measure if you are measuring density of water at ambient pressure, means room temperature, then you don't need to record the pressure. But if you are doing the PVT, for example, PVT study, in this case, the density will vary a lot. Okay, so you have to write down the pressure and temperature. You took pressure and temperature at which you measure the density of water and oil. The dimension of density is kilogram per meter, cubic meter in SI, or a pound per cubic foot in the English system. Now, what is the difference between liquid specific gravity and liquid density? If you look here at the last sentence, The dimension of density is kilogram per cubic meter. But for liquid specific gravity is a ratio of weight of a volume of liquid to the weight of an equal volume of water at the same temperature. So it has no dimension. That is the difference between liquid specific gravity and liquid density. It has no dimension. Okay, now that was the viscosity. Sorry, density. As I said, we measure liquid density and liquid viscosity. Why we measure viscosity? Because we use that value to obtain the permeability, and we measure density to obtain pore volume and porosity later on. So viscosity is defined as the internal resistance of liquid to flow. Viscosity is defined as the internal resistance of fluid to flow. As you can see here, this fluid flows well, so viscosity is low. And this liquid here looks like honey. The viscosity is high, so it can hardly flow. It can hardly flow. Of course, the viscosity of liquid usually rises with temperature at constant pressure. Rises with them. So the higher the pressure, the higher the yes. So viscosity of liquids usually rises with pressure at constant temperature, and that if and the viscosity will decrease as temperature increases. Water is an exception to this rule. The viscosity decreases with increasing of pressure at constant temperature. For most cases of particle interest, however, the effect of pressure on viscosity of liquid can be ignored. Okay, because the effect of temperature is much more higher. Pressure will affect the viscosity of gases. So for most liquids, it is ignored. Okay, a decrease in temperature causes the viscosity of liquid to rise. Effect of molecular weight on the viscosity of liquid is as follows. The liquid viscosity increases with increasing molecular weight. The liquid viscosity increases with increasing molecular weight. Okay, now how can we measure viscosity? How can we measure viscosity? I will talk about three types of viscosity measurement. The first one is capillary tube viscometer. You can call it U tube because the shape it has the U shape. And then there is the falling ball viscometer, and then there is the rotational viscometer. For the low viscosities, we use capillary type viscometer. For example, if you want to measure viscosity of water, of brine, okay, you can use the capillary type. If you want to go higher, if the viscosity is higher, like crude oil, for example, you go for falling ball. If you are measuring the viscosity of cement, for example, then you will go for rotational viscometer. Usually, rotational viscometer is rarely used in core analysis. We mostly use the falling ball and capillary pressure. And as you can see here, there are two types of flow. The first one is linear flow, and the second one is turbulent flow. So the capillary type viscometer, as I said, sometimes you can call it U tube because it has the shape of U. How can we measure the viscosity? Here you fill the tube. You fill the tube. Can you see this letter A? There is a mark. So you fill the tube and then you use a vacuum bulb to rise the liquid level here to this area, like higher than the mark A. Okay, and then you release it. So you release the vacuum bulb. So liquid will start falling down. Once the liquid reaches the mark A, you start your chronometer, and then you keep counting the time until liquid flows or reaches the point B, and then you stop it. That will be the measurement. Okay, that will be the measurement. So it is you are measuring the time that the liquid takes to move from point A to point B. After that, you take that number and multiply it by the constant of the viscometer, and that is the viscosity in centistock. You take that viscosity, that is the, you take that number, the value, the viscosity in centistock, you multiply it by the density of fluid, and you will get the viscosity in centipoise. Okay, so you first measure the static and then the dynamic. I'm sorry. Okay, dynamic viscosity. Now, as I said, if our liquid has high viscosity, higher than water, okay, we use the falling ball viscometer. And this type of measurement is based on Stokes law for a sphere falling like a sphere. Can you see that ball here in the middle? We measure the time that this sphere takes to move from this mark to this mark. Okay, so of course that ball is made of steel and it is polished and dropped into a glass tube of course, the diameter of that tube is a little bit larger than the diameter of the ball, so the ball will not be in contact with the tube itself. Okay, and then at constant velocity through a specific distance between, as I said, polished steel ball is dropped into a glass tube of a somewhat larger diameter containing the liquid, and the time required for the ball to fall at constant velocity through a specific distance between reference mark is recorded. The rolling ball viscometer will give good results as long as the fluid flow in the tube remains in the laminar range. In some instruments of this type, both pressure and temperature may be controlled. Pressure and temperature may be controlled. So sometimes this you can elevate. Of course, even this one you can elevate only temperature, not pressure. You can place it in a water bath. The third and the last is the rotational viscometer, and this one is used for non-Newtonian fluid. For example, the slurry. Okay, it is used in with our colleague with the cement department. Okay, they use it to measure the viscosity of cement slurry, and it of course it does not measure the viscosity directly. It measures the torque that the motor has to produce to move this fan here. Okay. Okay, with that done, we can now take our samples from the oven and start what? Start measuring the porosity. What is porosity? Porosity is the ratio of pore volume to bulk volume of the sample. Ratio of pore volume of the sample to the bulk volume of the sample. And as you understood, porosity is dimensionless because it is a ratio. It's a volume over volume. As you can see here, Starting from the right, high porosity. I can see high porosity, also high permeability. And you can see here connected pore spaces. For example, this big vug here is connected through this throat to this vug here. So that is good porosity and good permeability. And look at this, the picture in the middle. I have good pores. Porosity is good. However, permeability is very low. Why? Because those pores are barely connected. And I think most of them are not connected. So even we have good porosity, permeability will be low. And if you look at the third one to your left hand side, it is low permeability, very low permeability. Why? As you can see here, I have only small pores connected or not connected. They are still very small. The volume of those pores is very small. Okay, so here I have high porosity, high permeability, medium porosity, low permeability, and here I have low porosity, low permeability. As you can remember, I said this porosity here is good, permeability here is good because the pores are connected, but here pores are not connected, and that takes me to the types of porosity. Types of porosity. I have two types. The first one is the total porosity, and the second one is effective porosity. For what is total porosity? It is the ratio of all the pore spaces in a rock to the bulk volume of the rock, or I would say the sample. Okay, the sample, because we are talking about the core sample. So total porosity is the ratio of all space, all pore volume, all pore spaces in a rock to the bulk volume of the rock, whether they are connected or not connected. Now, effective porosity is the ratio of the interconnected void spaces to the bulk volume. Only the interconnected. And to measure the effective porosity, we use any kind of saturation. Any kind of saturation method. Saturation with gas like helium or nitrogen, saturation with liquid like, for example, brine, formation of brine, for example, or distilled water, anything. Or else we can saturate the sample or like do the what is that, mercury intrusion. So we saturate or we fill the pores with mercury. So to obtain the porosity or the pore volume in the effective pore volume or effective porosity, we have just to fill the pores with some liquid, and we measure the volume of that liquid, and by that we obtain the volume of the pores. But in total porosity, we have to crash the sample, and we will talk about that later on. So, as I said, we have two types of porosity. Also, we have two classification of porosity. Two types and two classification. What are the classification? Primary porosity and secondary porosity. Primary and secondary. I forgot to say something. Effective porosity is always less than total porosity. Less or equal to. Now, for porosity classification, there is primary porosity and secondary porosity. What is primary porosity? It is developed during the deposition of the sediment. Okay, secondary porosity is caused by some geologic process that happened or that followed the deposit, like, for example, fracture or dolomitization. Okay, that is secondary porosity. And secondary, secondary porosity will enhance the porosity of the sample, or like enhance porosity of the rock, will make it bigger or higher. Okay, as you remember here, the porosity is the pore volume divided by bulk volume. Okay, what is bulk volume? What is bulk volume? Bulk volume can be measured in two ways. Depends upon the shape of the sample. If the sample has regular shape, for example, right angle cylindrical shape, then we can measure the length and diameter, and we obtain the bulk volume. But if the sample is irregular, the sample shape is irregular, like what you can see here, then we can go for either saturation or paraffin, like dip it in paraffin wax, or we use the mercury. The most used method for irregular shape is mercury. That is why I'm going to talk about it. The pore volume measurement using the mercury, as you can see here, it is a scheme that is helium. Helium porosimeter. Later on, when we reach the capillary pressure, I will show you how to measure the bulk volume by mercury and mercury intrusion. So we said that porosity is the ratio pore volume over bulk volume. Now we talked about how to obtain the bulk volume. Okay, طيب. How to obtain the pore volume? For pore volume, as I said, you can inject whatever you want in the pores. You can inject helium, nitrogen, usually helium. The porosity measured by helium is higher than porosity measured by nitrogen, because helium molecule is smaller, so it penetrates the very fine, the very small pores, and it will produce higher value of porosity. And usually we use the P1 V1 equals P2 V2. That is the general, what is that? General law of gases. And we can also measure or obtain the pore volume of the sample by water saturation. Water saturation. As you can see here in this picture, this is the vacuum and the pressure water saturation. Vacuum and pressure water saturation. In this case, what we do is we take the sample. It could be regular. The shape could be regular or irregular. We take the sample. Of course, the sample should be clean and dry. We take the weight before saturation, then we place the sample here in this cylinder. Then we start pulling the vacuum. Usually we pull vacuum for 8 hours. Okay, then until the sample, there is no air in the whole system. There is no air in the whole system. Means no air here, no air here in the lines, no air in the cylinder, and there is no air in the pores. And then we open this valve, so brine will be sucked from this container into the sample. Now the sample, because it will be sucked, so the pressure will be equal outside the cylinder and inside the cylinder at like regular one atmosphere, one atom. So now the sample is being sucked in water. The sample is not pressured yet. After that, we apply pressure up to 2000 psi. By that, we guarantee all pores, even small pores, have been invaded by the water, formation water or distilled water, whatever you want to, whatever your plan is. Okay, then you keep the sample like that for another 8 hours or overnight. Then next day you release the pressure, open this cap, take the sample and take the weight of the sample, and by that, so you subtract the weight, the weight of saturated sample minus weight of dry sample divided by the density of that liquid, you will get the volume of the liquid that is inside the pores, which is the pore volume. Okay. Now, then the next one here is the mercury. Here is the mercury, like the what is that? Mercury pump. Okay, we use that mercury pump to um, sorry, we use that mercury pump to obtain the bulk volume and the pore volume also. So the mercury pump also will be connected to a vacuum pump. You place your sample here. Here in this area, there is mercury. Okay, and this is the sample here. Okay, and then you pull vacuum for several hours, and then you inject mercury and see what is, you can read here on the pump, you can read the volume of mercury injected into the pores, and by that you will obtain the pore volume. Okay, so now we know the pore volume, we know the bulk volume, we can get the porosity. Okay, that is done. Now we are done with porosity. Now, since our sample, this sample has been already saturated with brine, we can obtain the electrical properties of the sample. We can get the electrical properties of the sample, mainly resistivity. And if you remember what I said about of course you remember what I said about pore volume and porosity. Pore volume is a volume. It's a value. Porosity is not a value. It is dimensionless. So it is a ratio. Now resistivity also is a ratio. What is the difference between resistance and resistivity? Is like the difference between pore volume and porosity. If you look here closely to the picture, you will see a core sample. Of course, that core sample is saturated. That is our core sample, saturated with brine, and placed between those two poles. And now we are measuring the resistance of the sample. After that, we apply some calculations, and from the calculations, we will get the resistivity. Resistivity of the rock depends upon those. The first one is salinity of water. So if the salinity of water is high, then resistance is low. Temperature, if temperature is high, resistance is high, resistance is low. Porosity is high, resistance is low. Why? Because the sample will have more liquid, more formation, brine. Pore geometry, if the pores are big, then resistance is low. If pores are small, resistance is high. The formation stress and the composition of the rocks, because if we have as you can see here, this is a limestone. Okay, the resistance of limestone is different from resistance of sandstone, for example. So all of that will affect the resistivity. Now, why we measure the resistivity? Because we want to obtain the following. The first thing we want to obtain by measuring resistivity is the formation factor. Formation factor. What is formation factor? It is the most fundamental concept considering electrical properties. It is our ABC when we study the electrical properties of the rock. Okay, is the formation factor is defined by Archie as follows. As you can see here, F, sometimes you will see FF or FRF. All of them are formation factor. FRF or FF, all of them are formation factor. It is RO over RW. What is RO? RO is the relationship between water saturated sample conductivity and bulk water conductivity. Okay, so RO is resistivity of rock when the rock is 100% saturated with brine. RW is resistivity of brine. RO is the resistivity of the rock or the sample when it is 100% saturated with brine. RW is the resistivity of brine. Of course, all those measurements should be taken at the same temperature, or else you can do the correction. Okay, so after measuring the formation factor, we measure or we calculate the resistivity and index. Resistivity index. What is resistivity index? It is I, or sometimes you will find it RI. Both are correct. It is. RI is RT over RO. Do you remember what RO is? RO is resistivity of the rock or of the sample when the sample is 100% saturated with brine. RT is the resistivity of the sample when it is partially saturated with brine. Means it is if the sample is 100% saturated with brine, then the measurement is RO. If it is anything else, then the measurement is RT. Of course, RT will be higher than RO. Okay, what is the third component? What is the third property, electrical property? It is the torosity. Torosity. What is torosity? Torosity can be defined as LA over L to the power of 2, where L is the length of the core. L is the length of the core from here to here. Okay, LA represents the effective path length through the pores. So LA is always higher than L. That this is L from here, from top to bottom. But LA is the path going like this. So it is always greater or equal to L. Okay, based on simple pore model, the following the relationship can be derived like F, the formation factor, equals to torosity over porosity. Torosity over porosity. So if we calculate F factor from here, we can, and we calculate porosity from saturation, from when we saturate the sample, we can obtain torosity. Okay, the next component or property is the cementation factor. Cementation factor, look here, is F equals to phi is porosity, to the power of minus M. That M is the cementation factor. That M is the cementation factor. So cementation factor, Archie suggested a slightly different relation between the formation factor and porosity by introducing the cementation factor. So cementation factor is cementation factor is the relationship between porosity and formation factor. Okay, later on, I will ask you a question. If the porosity is high, what do you think about cementation factor? Is it higher or lower? Think about that. And later on, before you start asking me question, you have to answer this question. Okay, so if the porosity is higher, what will happen to the cementation factor? Is it higher or lower? Now, the next property, and it is the last electrical property, is the saturation exponent. Saturation exponent. It is I or Ri. Sometimes they call it Ri. Saturation exponent, the famous Archie's equation, gives the relationship of resistivity index with water saturation. Do you remember the resistivity index? What is the resistivity index? This I. What is I? It is RT over RO. RT over RO. But the saturation exponent is N, this one here. This one here. Okay, so here is another question for you. Before you ask me questions, you have to answer this question, please. If the water saturation is higher, do you think N will go up or down? Up or down? So if the sample is 100% saturated with water, do you think N will be higher or lower than if the sample is partially saturated with water? Now, by that, I conclude the electrical properties. Now, I will go to sorry, I will go to another property that is measured by core analysis, which is surface tension and interfacial tension. Surface tension and interfacial tension. What is the difference between those two? Surface and interfacial tension of fluid result from molecular properties occurring at the surface or interface. Surface or interface. Okay, surface tension is the tendency of a liquid to expose a minimum free surface, like this one here. This one here, okay? Surface tension may be defined as the contractile tendency of liquid surface exposed to gases. And surface tension is responsible for water evaporation or liquid evaporation. For example, if you drop a few drops of water on the table, after 1 hour, those drops will be vanished. Why? Because they evaporate. Why? Because of the surface tension. Okay, because of the surface tension. Now, the interfacial tension is a similar tendency which exists when two immiscible liquids are in contact. See here, this drop here is on the top, so there is only surface tension. Here, of course, this drop is still water. Suppose this is water, this here is still water, so there is no interfacial tension unless this drop is this liquid is different from this liquid. So the relationship between them will be interfacial tension. Interfacial tension. Suppose this is a drop off. Suppose this here is oil and this drop is water. So the relationship between this liquid and this liquid is the interfacial tension. Okay, that's it. That is the difference. Now, why I said, suppose this is oil and this is water, because as you can see, this drop is sinking, so it is heavier. Now, how can we measure the interfacial tension? We can measure it. We can measure it in different ways. The first one is capillary rise method, as you can see here. Okay, or Willemly plate method, ring method, drop weight method, pendant drop method, and spinning drop. The most used methods are those two: pendant drop and spinning drop. Pendant drop and spinning drop. For interfacial tension, if for the low values of interfacial tension, spinning drop is more accurate than pendant drop. Okay, so the spinning drop device has been widely used in recent years to measure very low interfacial tension. That we use that, okay, that is very important when we are running a study of enhanced oil recovery, especially enhanced oil recovery by surfactant flood. Okay, because when you add surfactant to the water, interfacial tension between oil and water will be very low, like 0.0001, for example. And it is too difficult to measure it by bend and drop. It's almost impossible. Okay, so we use the spinning drop. So if you are measuring the interfacial tension between crude oil and water, it will in like formation water, it will range between 7 newton per meter, between 7 and 23. Okay, for pent and drop, that is fine. But when you add the surfactant, it will drop below zero, a lot below zero. Okay, so it is better to use the spinning drop. Now, what is the relationship between contact angle and wettability? I want you please to look at, sorry, I want you please to look at this picture here. Okay, I want you please to look at this picture here. I hope it is clear for you to read. Okay, starting from uplift, low surface energy, low surface energy. And that means this drop of water and this rock are not friends at all. This water hates this surface. Okay, so it takes the spherical shape because this drop wants to keep the contact between between sorry, the shape is spherical because the drop wants to keep as minimum as possible the contact between itself and the surface. But when the drop loves the surface, then it will hug the surface. It wants to make the contact surface as big as possible. So here you can, if you want to measure the contact angle is obviously higher than 90. It's almost 135. But here the contact angle is like maybe 15. Okay, so for this, if this drop is a water is if this drop is water, then this surface is oil wet. Now, if this drop is water, then this surface is water wet. For you as a reservoir engineer, you want your rock to be this type. You want so if you are a reservoir engineer, you want your rock to be this type because you want the rock to be water wet, not oil wet. Okay, so here in the first case, the liquid will wet the solid completely. Okay, whereas the later case is contact angle is higher than zero, will develop between the surface and the drop. Okay. Okay, we said surface tension. Tension means it's a pressure. So here, sigma SO minus sigma SW equals to sigma SO cosine theta. What is theta? Theta is the contact angle. Okay, the adhesion tension, which is a function of interfacial tension, determines which fluid will wet the solid. In the case of water oil solid, we will have this. Of course, the SO is the solid oil, SW solid water, and cosine and theta is our contact angle. So let's go back to this picture here. If this is if this drop is water, as you can see, the contact angle is very small. So cosine, what will happen to the cosine is if the if the angle is small, cosine is small. So this this part of the equation will be also small. Okay, so from that we can see that it is oil wet if this was a drop of water. Now, the adhesion tension, it has three category or three, um, what is that? I would say category, three phases. The first one is positive adhesion tension. That means the surface is water wet. If it is zero, then it is neutral. It is not water wet, it's not oil wet. If it is negative, then the surface is oil wet. Okay. This property is very important when you want to run enhanced oil recovery test. Now, what is the importance of rock wettability? If you look here at those three pictures, please look closely so you can see green is oil, blue is red. Okay. If you look at this one here, water wet. Why? Because does not is oil is not contacting with the rock, which is good. As a reservoir engineer, we want that. We want the system to be water wet, so oil will not stick on the surface of the rock. Here it is mixed wet. It's oil wet and water wet. So you can see that water sticks on the surface of the rock as well as the oil. But if you look here, that is that is a big headache. Why? Because this system is oil wet. As you can see here, the rock particle is covered with a film of oil, and water is here in the middle. That means if you do flooding, if you flood this system with water, oil will stay in its place and only water will be moving. Okay, water will be moving. Now, since we talk about the wettability of the rock, let's move on and talk about the wettability of the reservoir rock. Wettability of reservoir rock system will depend on the following. First, reservoir rock material and pore geometry. Second, geological mechanisms like migration, for example, and accumulation of the rock particle. The composition and amount of oil and brine. Composition and amount of oil and brine. Because if in some types of brine, the interfacial tension will be low. Some types of brine interfacial tension will be high. Same as some types of oil interfacial tension between oil and brine will be higher and like by nature, or it will be lower also by nature. And physical conditions, pressure and temperature, especially temperature, reservoir temperature. And the last one is the mechanisms occurring during the production. mechanisms occurring during the production. For example, change in saturations, change in pressure, and change of composition of water. Okay, please note that it is difficult to make a general model of wettability, including all those factors. Although a lot of work has been done on wettability, it's not fully understood how the wettability of a porous rock surface is composed. Okay, now we talk about wettability and importance of wettability. Let's talk about how to measure wettability. How to measure wettability. As you can see here, this instrument, it is the amot tube, and from the picture only, I can say that this sample is saturated with oil. This sample is saturated with oil and it is placed in water. And now we leave it there for several days or several months even. So oil will leave the sample and get together here. So we measure the amount of oil versus time. Okay, it is spontaneous. Oh, here, measurements on core sample, Amot method, and centrifuge method. Here is the Amot method. And or we can obtain the wettability by measuring or by measurement of contact angle. Okay, measurement or of the contact angle. As if you remember this picture here, okay, from contact angle we can decide whether this surface is oil wet or water wet. Okay, the next topic is capillary pressure. Now we are done with we are through with the sorry, with the wettability. I will talk a little bit about capillary pressure. So when two immiscible fluids are in contact when two immiscible fluids are in contact in the interstices of a porous medium, as you can see here, the one fluid will rise and the other one will not. As you can see here, suppose this is a rock sample, okay? Here I have good porosity, big pores. Here I have small pores. So the capillary pressure here is low, capillary pressure here is high. And that is very important when you want to put your well into production and you want to do purification. So you cannot pull it here, because if you pull it here at this depth, you will produce only water. So you have to calculate the capillary pressure, and then you can calculate where to put your pullet. So you cannot make them here, you cannot make them here, otherwise you will produce only water. And that is the importance of the capillary pressure in the reservoir. Here in this picture, you can see the typical capillary pressure curve. Of course, it is impossible to obtain such like piece of art in the lab. This is identical or typical, okay? This one is drainage and this one is imbibition. And when I say drainage and imbibition, it's not water replacing oil or oil replacing water. It is wetting phase replacing non-wetting phase, or non-wetting phase replacing wetting phase. Please be careful to that, because sometimes if you say water replacing oil, could be imbibition and could be drainage also. You are not sure until you know you know which one of those is your wetting phase. Now, how can we measure the capillary pressure? We can measure the capillary pressure by two methods. The first one is sorry, we can measure it in four methods. The first one is the porous plate, as like this one. But the problem with it's very accurate. However, it takes long time, very long time. And the centrifuge method is good. It is fast. However, if you are running the sample at ambient pressure, then you might lose the sample. It will break. Now, mercury injection is very quick, it's very accurate, especially if the mercury pump rise the pressure up to 20,000 psi or 60,000 psi. It's very accurate. However, the sample, you can take only small sample, like a small piece of a rock. Okay, that means you have to measure a big amount of samples, and then you take the average. So your measurement will be representative. Uh, Also, there is another problem with the mercury injection, that is the sample will be destroyed. You cannot use the sample to do anything else. After inject mercury into the sample will be destroyed. Okay. Now our last section is permeability. Last section is permeability. Do you remember this picture? Good porosity, good permeability, good porosity, low permeability, low porosity, and zero permeability, I would say. Now, I have another question for you. When you open your microphone to ask me a question, I want to ask you, what do you think the permeability of clay? Is it high or low, and why? Okay, keep that in mind. The permeability is a property of a porous medium. See, permeability, absolute permeability, is the property of the porous medium, and it is a measure of capacitance of medium to transmit fluid, to let the fluid flow. Okay? Now, you can, or we can measure permeability to liquid. We can measure permeability to gas. To gas, if you want to measure permeability to gas or gas permeability, you have to keep in mind the Klinkenberg effect. The phenomena of gas, which is gas slippage. The phenomena of gas slippage occurs when the diameter of the capillary openings approach the mean free path of the gas. So it is too narrow for the gas, but the gas can still go through. Okay, that is the meaning of this. It is too narrow, but gas can still go through. Okay, that is the gas slippage. Of course, that does not happen with liquids. The mean free path of gas is a function of molecular size and the kinetic energy of the gas. You remember when I said when you measure porosity by helium, you get higher value than measuring porosity by nitrogen. Why? Because the molecular size of helium is less than the nitrogen one. Therefore, permeability of gas depends on factors which influence the mean free path, such as temperature, pressure, and the size of the gas, molecular size of the gas. So here is another question. If you measure permeability by air and measure permeability by helium, which one will be higher? Which one will be higher? If you look at this deeply, you will get the answer. Okay, now we have measured the sample, the permeability of the sample by nitrogen, for example. Now our sample, as I said, is saturated with water, so we can measure the permeability of liquid or liquid permeability. To measure liquid permeability, there are two types. The first one is the variable head permeameter and the constant head permeameter. I know it's a big word. However, it is constant pressure or variable pressure. That's it. Okay. Are you injecting water or brine at constant pressure or constant flow rate? If you are injecting at constant pressure, you are here. If you are injecting in a constant flow rate, you are here. Okay, so that is the measurement, not how we measure permeability. It is the measurement of permeability. Okay, now we have, you remember the two types of porosity, absolute porosity and effective porosity. Same thing goes for permeability. We have absolute permeability, effective permeability, and relative permeability. Absolute permeability, when the sample is saturated with brine and you are injecting the same brine, or sample is saturated with oil and you are injecting the same oil. Okay, so absolute permeability, you will measure absolute permeability if you are flowing the same saturant through the sample. Okay, but if the sample is saturated with 100% saturated with water and you are injecting oil, then this measurement is called effective permeability because you have two phases, regardless whether they both phases are flowing or the sample is at irreducible water saturation, means water is not moving, only oil is moving. That is still effective permeability. Okay. Now the ratio is the relative permeability. Relative permeability is influenced by the following. First one is saturation, water saturation, gas saturation, and oil saturation. Of course, we can run the relative permeability test for example, liquid or liquid gas. Okay. The first one, the first parameter is saturation. Second parameter is saturation history. Saturated with water, then clean, then saturated with oil, then oil was displaced with water, then the sample was aged, then flood again with water. That will affect the permeability. Why? Because it will affect the wettability. That is the wettability, speaking of which, okay? And it will be affected by temperature. Why? Because permeability is affected by viscosity of the liquid or the fluid. So, and viscosity of fluid is a function of temperature. That is why temperature will affect the relative permeability. Viscous and capillary forces. Okay, and gravitational forces. Now, if you are running your relative permeability test by centrifuge, this will be 0. Okay, and pore geometry. Are the pores all big, all small, very some big, some vague, some small? The pore throat is the pore throat symmetric? Is it not? All of that will play a big role in relative permeability. And if you can see here, that is the key RO. Key RO means oil. If you look here, that is water saturation. Now water saturation starts from 0.2 and it goes up to 0.8. And for the key RO, this line This line, the red one, is the effective permeability of oil, and this one is effective permeability to water. So if you look at this plot, do you know, can you tell me, is that water flooding or oil flooding? Is that oil flooding or water flooding? Before asking me any question, answer that question. Okay, so how can we measure the relative permeability? We can measure relative permeability in two methods. The first one is steady state. The second one is unsteady state. In steady state method, the sample will, for example, saturated with brine, and then you inject water and you inject brine and oil simultaneously through the sample. Okay, and then from that you will go, you will start your measurement. Okay, that is very briefly, because later on, inshallah, if you hopefully if we have the scale alone or relative permeability alone session, then I will have more time to talk. So for steady state, you inject both phases into the sample. In unsteady state, you inject only one phase. For example, your sample will be saturated with brine, and then you inject only oil. Of course, you will start producing brine, and then there will be breakthrough. So the effluent will be oil and the brine. Then the amount of brine will decrease, the amount of oil will increase until there is no more water coming out of the sample, and then you are at the SWI. And at that point you stop the measurement. Okay, so that is the steady state. In steady state, as you can see here, you inject both phases together. In unsteady state, you just inject one phase. So the sample is saturated with brine, you inject oil. All the sample is saturated with oil, and you inject brine. Here are the disadvantage of the unsteady state. Relative permeability data will not be over the entire saturation range and might, in the extreme case, be restricted to the endpoint data only. Second, discontinuities in capillary pressure at the core ends may lead to distortion of pressure data and recovery measured. For this disadvantage, the core lab implemented the composite core flooding. Composite core flooding. Okay. Now, the third disadvantage is substantially more calculation are necessary, but the mathematics may be solved by computers. So we have computers. Okay, so as I said, unsteady state is much faster. However, steady state, calculation of steady state is much more easier, but it takes long time, months maybe. Okay, for unsteady state, it will not take that much time, maybe 2-3 hours, depending upon the permeability of the sample, but the calculation are a little bit more difficult, I would say. By that, I conclude my presentation. So I want to say thank you for your attention. Now the floor is open for